Hello and welcome back. In 11.1 we get to start working with the nature of probability. And this is going to lay some of the foundation for our work throughout this chapter. Start with a couple of quick definitions, an experiment, a controlled operation, yields a set of possible results. So how can the experiment end? The possible results are outcomes. Of the experiment. An event is a subcollection of the outcomes. So for example, you can have an experiment. Draw one card from a deck. So that's our experiment. We are assuming we draw it randomly. An event might be that we select a king. That event can actually happen from 4 outcomes. We could have drawn the king of hearts, king of diamonds, king of spades, or king of clubs. That is one ugly looking little club there. Yeah, this guy's pointy, that guy's rounded. So there are 4 different events, 4 different outcomes. King of hearts, king of clubs, king of spades, king of diamonds. Those outcomes make up that one event. Any of those could be part of that one event. There are 2 broad categories of probability. We have empirical and we have theoretical. We'll call the event cap E. Notation then, probability of event E. That would be denoted with a capital P, not a lowercase p, P of E. So we'll start with empirical probability. This is also in some books referred to as experimental probability. So for our experiment, going to randomly select a number, specifically an integer. From 1 to 10 inclusive. And our event for this experiment will be that we have an even. And we're going to do this experiment, let's say, let's do this 10 times. Okay, so my random number generator, I'm just going to use the built-in feature of the TI. Actually, that's focused fairly well. So in the math menu, if you're working with any of the TI graphing calculator series, math menu, go over to probability at the top, random integer, option number 5, and we give it the bounds, which are assumed to be inclusive. All right, so we've selected an 8. You can't see the edge of my 8 since my calculator, as you can see, is a little bit on the older side. All right, so of the 10 times, we selected an 8, a 6, a 7, 4, 5, a 10, a 5, a 9, a 6 again, and a 2. So remember, an event would be that we had an even number. So the probability of an even, again, under the empirical headline, empirical probability of this event, we drew 10 numbers. So the bottom is just the total number of experiments. The top was the times the event occurred. So in even, we had 1, 2, 3, 4, 5, 6 evens. So 6 out of 10, or 3/5. So notice that that isn't exactly what we would expect to see necessarily if we had run the experiment 10 times and half our numbers were even and half were odd. We would have expected that to be 5 out of 10. Empirical, you'll get some deviation from what you sort of expect. What you expect to see would be more the theoretical probability. Some other things we can draw from this experiment, though. What was the maximum number of evens? Well, we performed the experiment 10 times. The maximum number of times we could have gotten that was 10. So that means the probability, had we seen that, so this is if we saw 10 evens in 10 draws. 10 out of 10 is 1. So 1 is the maximum probability. So something that happens every time your fraction will simplify to 1. The fewest number of evens we could have seen 0. None of them. Probability in that case would be, I don't need the parentheses there, 0 out of 10. 0 out of 10 simplifies to 0. This is the minimum probability. So probability of event E is always between 0 and 1. So please, please, please remember this fact. You won't see us mathematicians claiming that something is an always statement very often. This is always between 0 and 1 if you're talking probabilities. 100% of the time, your probability will land you between 0 and 1. So please don't give me a paper saying that your probability is 2.3. Not possible. Can't be a -4. Not possible. Always, always, always between 0 and 1. So let's say we do another experiment. This one, let's say in the medical field, and we're testing a new drug. So let's say we tested on 1,000 patients. 416 saw their condition improve. 312, no change. And 272 felt worse. So this is another example where we would see empirical probability being used in the real world. So if our event is that the patient improves, then P of E would be 416 out of 1,000. Let's see if we can simplify that. So that would be 104 out of 250, which would be then 52 out of $1.25. Again, that is on the required interval of 0 to 1. In other words, it's either 0, 1, or a proper fraction. You'll see this used in genetics as well. The famous Mendel's peas experiment. So our dominant trait in the type of plants he was working with was that they turned out yellow. Recessive was that they turned out green. And let's say that he bred pure yellow with pure green. So each plant only has genes for the listed color. So each plant now has one of each color. And let's say that after he runs this experiments many, many times, the yellow he counts up, he has 3,394 plants. Among the offspring, the green, he has 1,115. So then the probability of yellow, so it's not always a cap E, sometimes it's cap Y for yellow. Will vary depending on the experiment. So how many times do we see that outcome out of how many times did the experiment come to a close? So 3,394 out of 4,509. And notice if you do the division on that, a decimal approximation, that is close to the 75% that you would expect from your biology class. Approximately 0.752717. I'm not really looking for approximations though, unless otherwise specified. I'm looking for the fractions. Now, one more important idea in the empirical side of probability is the law of large numbers. More times you run an experiment, closer the empirical probability gets to real probability. So your insurance agent doesn't know for sure that you're going to file a claim during the billing period, but they do know from the law of large numbers what the likelihood of that is based on thousands and thousands of clients. That's why there are no small insurance companies. There are small brokers that work with large insurance companies. Risk pools need to be large in order to use the law of large numbers to effectively set rates. Otherwise, a small run of unexpected events would basically wipe the company out. That's also, by the way, how casinos stay open. They don't know the outcome of an individual roll or an individual draw of a card, but people that know way more about math than any of us, myself included, have run all the numbers through, and they know over time exactly how much they should be making on average per play of the game. So this gets us then into the idea of the other kind of probability, the theoretical probability. So theoretical probability, this is for the rest of the chapter what the author means when they say probability. Unless otherwise specified. So this time, instead of actually running the experiment, we're just going to say, okay, what should happen based on what we know. So let's see, we'll do an experiment where we roll a die. So standard die has sides 1 through 6. Die is the singular of dice, by the way. So for example, if I roll a single die, probability of rolling a 2, there's one side that has the 2 out of 6 sides total. So how many outcomes have our event if they're equally likely? Out of how many ways can the experiment draw to a close? I can look at the probability that I have rolled something less than or equal to 4. So there are 3 events that qualify for that out of 6 total. Probability that my roll is less than 100. 6 out of 6. Every single side of a die is less than 100. That's an event that will happen all the time. I could ask for the probability of rolling an odd. There are 3 odds out of 6 sides. Probability of rolling a 7. If I'm rolling only a single die, I only have 1 to 6 to choose from, 0 to 6, which is 0, the minimum probability. One other nice property that we have with these probabilities, sum of all possible outcomes is 1. You have to cover 100%. So for example, the probability of rolling a 1 if we continue our die experiment, plus the probability of rolling a 2, plus the probability of rolling a 3, etc. That would be 1 6 plus 1 6 plus 1 6. They're all going to be one side out of 6, which is 6 6, which is a 1. Another frequently used example in probabilities is cards. So for those unfamiliar, I'm going to do just a quick rundown of what we have in a deck of cards. $52 cards, 4 suits, hearts, diamonds. These guys are called clubs, and these guys are called spades. Hearts and diamonds are red, clubs and spades are black. Cards, we have the ace, 2 through 10, jack, queen, and king. Jack, king, and queen are what are referred to as face cards. So for example, the probability of selecting a queen, there are 4 queens in the deck out of 52 cards in the deck total, which will simplify to 1/13. Probability of selecting something that is not a queen. There's 2 ways to do this. I can count up all of the cards. So there would be 48 cards that are not queens. out of 52 cards total. That will reduce to 12/13. Or I could have done this a different way. I could have taken 100% and taken off the queens. Which will still lead me to the same 48 out of 52, which will still reduce to 12/13. That's borrowing off of this idea that the sum of all possible outcomes is 1, and every card is either a queen or not a queen. So I've covered all of the events. So if you want a more general write-up of that, probability of A plus probability of not A is always a 1. You can also see that rearranged with just a little algebra. Probability of not A is 1 minus probability of A. The probability of a club. There are 13 clubs out of 52 cards in the deck. That will reduce to 1 and 4. And that should make sense. Each suit is equally represented with 4 of each cards. All right, so in 11-1, I would try out 1 to 10 all and 11 to 77 on the odds. And again, in this section, make sure you're watching out for theoretical probability versus empirical probability. If you have any questions, please get in touch. Otherwise, I will see you next time. Stay safe out there.